Hello everyone, welcome back. Now I want to take a look at the quotient rule. Basically, if we compare it to the product rule, it's a combination of two functions divided. So normally you'll see it in fraction form, but the division symbol could be there as well. Again, that could be bracket over bracket, or just polynomial over polynomial, or any function that has at least one x term on top and one x term on bottom. You could use quotient rule. So quotient rule proof we'll look at again briefly. However, the rule itself has some similar characteristics to the product rule. The first is the quotient rule does give you a new quotient. So when you're setting it up, if we look at it like we did the product rule, you've got f of x and g of x. So they work the same way. Derivative of the numerator, so f of x, times the denominator, minus the derivative of the denominator times the numerator, always subtraction, always over the denominator squared. So that's kind of automatic. When you see a denominator, you can just put it in your derivative and square it. The numerator part is the situation that's very similar to the product rule. Instead of adding, we subtract. Right? So if we look at it that way, it's the product rule subtracted on top, right? If we call them 1 and 2, right? So you get the derivative of 1 times 2 minus 1 times the derivative of 2, rather than using f of x and g of x, right? So the derivative of top times the bottom minus derivative bottom times the top, all over the bottom squared. Kind of just an easy way to remember. The proof, as you can see right away, once you put in fractions into the limit definition where you're dealing with x plus h and f's and g's, it does get messy. And similarly to the product rule, there's this part in the middle that we have to put in to equal 0, or negative f of x g of x plus f of x g of x, but it helps us factor in order to get the derivative notation we need. So if you just look at this part and we scroll down to the factoring part, you can see here at the bottom that what's happening is when we factor out our 1 over g of x plus h and our 1 over g on this side, it is a tangly proof, and eventually we'll get to the rule. But with the inputs and the factoring at the bottom, you see that it's g of x times the derivative of f of x over g squared x minus f of x times the derivative of g of x over g squared x. And that turns into g of x f prime x minus f of x g prime x all over g of x squared, because essentially this is a common denominator. Don't worry too much about the proof. If you can look through it and kind of figure out how it works, awesome. But when it comes to you having to reproduce a proof, the only time you would be asked to do that is on your CPT, or if you do Math 1000 in that exam, and they narrow down which proofs you would be expected to do. This is a very time-consuming proof. This is not one that I would expect to see on an exam, but understanding it is important. Now let's look at a couple examples. So if we jump to page 8, I just want to do these two for this video. So we look at the first one. We got a numerator and denominator. You can do that on the side. So if I were to do the derivative of the numerator, right, we use power rule now. We don't have to worry about that limit definition ever again when it comes to these more complicated problems. And then if I look at the denominator, it just gives me 2. So the derivative of the numerator is 3, derivative of the denominator is 2. The algebra part comes into play because we've got to leave the original values in there as well. So if I take that calculation, so derivative of the top, this is the way I always do it, derivative of the numerator times the denominator minus the derivative of the denominator times the numerator all over the denominator squared. So this is the automatic part. You see a denominator, you can square it right away. That's part of your problem. So the calculus here is done. Now we need to simplify. 6x minus 15 minus 6x minus 2 all over 2x minus 5 squared. The denominator sometimes we really can't do much with. We just leave it squared. The numerator here, we get 6x minus 6x cancels out. Negative 15 minus 2 would be negative 17 over 2x minus 5 squared. So that's how you would do that quotient rule. Bit of work to it. However, the derivative calculation itself is not overly complicated in this case. Let's look at another one. Down here, kind of take the same logic or same process I did up top. What is the derivative of root x? Because the 6 is a constant. So the derivative of negative root x would equal negative 1/2 x to the negative half. Right, from our examples from the power rule, that root value is always going to be half in front, and then 1/2 take away 1. Derivative of the denominator is going to be similar because we got another root down there. So 1 plus root x, the derivative of that would be half x to the negative half. So let's see what that looks like when we multiply it out. So derivative of the numerator, negative half x to the negative half times the denominator, 1 plus x to the half. So I'm going to change it to all powers. It'll be easier to multiply. X to the negative half times x to the half, and you'll see why in a second. Minus derivative of the denominator, so we got 1/2 x to the negative half times the derivative of the numerator. So that one's set up. Then that's all over 1 plus root x squared. And again, there's not much we can do with that. Now let's work with the numerator here. So negative half x to the negative half times 1 is just itself. So we simplify that into negative half x to the negative half. Then the second term is where some simplification happens. We get negative half x to the negative half times x to the positive half will cancel out. So that's essentially times 1. So we just get negative half. Minus half of 6 would be 3, and we're stuck with the x to the negative half. And then minus and times a negative is positive. And again, x to the negative half times x to the half would just leave me with the coefficient of 1/2. All over 1 plus root x all squared. Again, this first step takes care of the calculus. The rest is algebra. What do we do with this? Well, we can combine like terms, but first I want to get rid of the complexity in the fraction. So if I times everything by 2 on top and bottom, so on top if I double a half I get negative 1. Same thing here, I get negative 1. Double 3 to get 6. And then double a half to get 1. All over, if I multiply the top by 2, I got to multiply the bottom by 2. Now what do we get? We get negative 1x to the negative half minus 6, so that gives me negative 7x to the negative half. Negative 1 plus 1 cancel out. We're almost done. Sorry, I messed up that 2 there. That should be x with the squared outside. So with this here now, this negative half gets moved to the bottom because of the power rule. or negative power rule I should say, negative 7 over 2x to the half 1 plus root x squared. And I'm dragging this on a little bit, but I do want to show you all the possible steps. For the most part, if you stopped here, you'd be fine. Even if you stopped here in calculus, it'd be a good answer. But ultimately, this is a radical, so we would rationalize it. Negative 7, we times top and bottom by root x. We get negative 7 root x over 2x 1 plus root x squared. So the general rule is you'd rationalize a single radical, but this binomial squared, you wouldn't rationalize that. Right, so that's just a couple of quotient rule questions. Hope that helps. I'm going to post some information in the stream when I put up these videos on some practice that I'd like you to do between now and your next skill check. So if you have any questions or concerns, just post them in the comment sections or email me. Have a great weekend, and I'll be back with some new stuff next week.